Good afternoon. So we continue our tutorial here. So we go for question 1 to 15. So for example, we have a situation of this one. We have a fixed plate and a moving plate here. And then we need to calculate the velocity profile of uy with the power n as parameter and the velocity at the midpoint of h/2. So because this is the height is h, and we need to calculate what is the velocity of this one. Okay, so for n equals 0.5, 1.0 and 2.0. Okay. Okay, so in this question, so we not discuss about this n because we have another question that specifically discuss about this later on. So I just skip one. I just want to show how the velocity profile has been developed in this situation. So where we know we assume that the flow between the parallel plate like this. So we assume that the velocity for the moving plate is constant. So I mean there is no acceleration, and we assume that this situation is actually open in atmospheric pressure. So we assume that there is no pressure gradient. So and then we could assume that the shear stress is constant and the velocity gradient is also in constant. So this is the simple assumption. Later on in next question, we will have this kind of situation. So we will have we put the problem of n equal certain value. Okay. So and then because the idea of velocity gradient is constant, so we just assume that it is equal of du dy is equal to b. So the meaning of velocity gradient here is the difference of du dy. Okay, here you need to understand how to develop or how to write your own du dy, because in Navier-Stokes equation or the continuity equation, you will face any possibility. You may write du dy, du dx, and du dz. Both these three parameters is actually valid. Okay, but you need to understand is in this situation, okay, we assume that the velocity profile is like this. So means that the velocity of this one is different with the velocity at the middle one, and it is different with the velocity at the bottom point. So means that there are velocity changes according to the y-axis. That's why we write as du dy. Because normally students, they're quite confused. They start to write as du dx. Okay, du dx will means that this is the x-axis and the velocity here is different from here and different from here. So the du dx means that this is the condition at x-axis. Okay, normally when we assume du dx is equal to 0 because we assume our flow is steady flow. Okay, please make revision because we have a steady flow and uniform flow. And these two type of flow is actually independent. So mean you have steady and uniform flow, steady and non-uniform, and you may have unsteady and uniform, and then you may have unsteady and non-uniform. So that the idea of steady flow and uniform flow is independent. So they will have both. They will create four conditions, as I told you last night, just now. Okay. So means that we assume that we have du dy is equal to b, and then we rearrange our equation become du equal b dy, and then to get the total value or the final equation of the velocity, so we integrate both sides. So we integrate du, so it is equal integration of 1 times du, so it will give us u here, and then the integration of b dy. So we will have b is the constant, and we will get new terms of y. So we have by plus a. So the a here is the constant. Okay, so and then here we know that normally in equation, so we have y equal mx plus c. So and then we need to fulfill the unknown terms, which is the m and the c, and then we the final equation must be y equal 5x, for example, plus 7. So means that we need to make sure that our equation is full like this. So in this situation, our question must be only will have the terms of u and y. That's why we create the question asks us to find uy here, means the velocity of u in term of y coordinate. Okay, any question?
Yes, doctor,
Okay.
if you don't mind, I have two questions
Okay.
related to a tip. First, when we exactly assume that no acceleration, no pressure gradient,
Yes.
no shear stress, how can we know that there's no acceleration, no pressure gradient, and no shear stress?
Okay. Normally, if you have a situation like this, okay, you will give the assumption actually. In real situation means when you do master project and so on, you have the situation. Normally, you will start to give a condition, and
Oh, yeah.
you are determining it by yourself.
Okay.
Okay.
So about du over dy equal to b.
Okay.
From where we got this question?
Okay.
Can you clarify it, please?
Okay. So this is we assume that the shear stress is constant. Okay.
Okay.
Okay. The shear stress means we say that the liquid that we use between these two plates is actually Newtonian. So I think you know about the Newtonian
Yeah.
fluid.
Yeah.
Okay, we have the shear thickening, we have the shear thinning. So the
Yeah.
shear thickening and shear thinning is quite difficult to analyze because it's different. The behavior its behavior in exponential curve. Okay, we don't know. Okay, the
Yeah.
Newtonian is always linear. Okay, that's the idea. The shear
So
stress.
you mean it come from the same equation, tau equal mu du over dy, but
Yes.
we remove the mu and tau, right?
Yes, tau is mu du dy. Yes, because we assume that tau shear stress is constant, and also we could bring the mu here as a constant. So that's why we say du dy is actually the constant.
Okay.
Okay. Okay, thank you.
Doctor, can
Yes.
I have a question, please?
Okay.
Is there any indication to make these assumptions? Because you just said we have to start and some assumptions.
Yes.
These assumptions according to what, and how can we start this kind of assumptions?
Okay. So in chapter 2 and chapter 3, we will have some kind of this question. On that question is to they will mention it properly. Okay, but for this solution, this is a chapter 1. I just want to show you the how to integrate this one. That's one to give you a simpler terms. So I assume that everything is 0. So in chapter 2 or chapter 3, we will start to solve same condition like this, but we start with the Navier-Stokes equation. Okay.
Yes, but doctor, there must be some. I'm not talking about the mathematical wise.
Yes.
There be some physical rules or conditions that it will
Okay.
be an indication for us to make this kind of
Okay.
assumptions.
So if
It
you
would
want to know, okay, I will explain it.
be on some physical rules.
Okay, so the idea is simple. If you have a moving and a fixed plate like this, so if the moving fluid is, if you pull this normally, so in this situation, you pull the plate here, in constant velocity. If not, you will create acceleration. Okay, so the velocity here is constant, so means there are no acceleration. So and then normally we will use the idea of Bernoulli equation, because you know Bernoulli equation can be used for stream function for any flow, and Bernoulli equation can be used for incompressible flow. So mean if you dealing with fluid with a not flow in high velocity until 0.3 Mach number, or the density and everything is constant, means that you could deal with Bernoulli equation. So normally if you have situation of this one, you have a fixed and moving plate, we will use liquid inside this plate. Okay, because it is not easy to control if you put any gas here. So gas will vaporize and so on and so forth. Okay, we will, okay. So and then let's say, so from the Bernoulli equation, we could say that the level here is equal. So means we could neglect about the potential energy. So you know the Bernoulli equation, P over rho G and so on and so forth. So we could neglect the Z, the potential energy. So means the parameter for the Bernoulli equation is pressure and velocity. If you have constant velocity, so means for sure you will have a constant pressure, because you know increment of pressure will lead to the decrement of velocity. So mean if the velocity is constant, the potential energy is not changes, and then for sure your pressure is constant. So mean there are no pressure gradient. So please know that pressure gradient and pressure equal to zero, it's totally different things. Pressure gradient means there are no increment or decrement of pressure, but the pressure might be there, okay, but there are no gradient. Okay, so and then the shear stress here is assumed is constant, because normally we are dealing with the Newtonian fluid. Is that okay?
Yeah, it is. It is okay, doctor. But I see that we have made more than one assumption per one question, and that might be quite confused for dealing with this kind of questions. I mean, there must be something to be a basic for us to depend on on the assumptions to make the solution easier.
To make the solution easier. So this is the easiest solution, I think.
I'm just confused about the number of assumptions that we have in this question, maybe.
The number of no. So I think it's depend on the real situation.
Yes,
Oh,
of course, it should be.
I think you understand everything. Why we take there are no acceleration. Why we say it is no pressure gradient, and then why this shear stress is constant, and then so what confusing you?
No. I'm not talking about the straight statement, just like what they have said here. No acceleration. That's mean acceleration zero, pressure gradient. They mention it, but sometimes the statement will be manipulated, that you can just assume depending on what you have understand from the question.
Yes, actually you need to do that, because in chapter 2 you will make more assumption to simplify your equation.
Yes, yeah. Because I have seen this kind of a question, that's why I'm asking about this.
Doctor, actually, our problem is not about the steps and how we solve the question. Our problem is how to start and how to assume. That's all. Because the topic is quite wide, and there are a lot of assumptions.
Okay, so let's say you have this question and you don't know what to assume. Is
Yeah.
that your question?
Yeah. Not just that. All our lecture. Sometimes we face some assumption that we don't know how, when, and how we conduct it.
Okay. So so this is a chapter 1. So I try to pick up question from the our textbooks, and might be for question 1 to 10 is quite a very wide. So we are talking about the temperature, the ideal gas law, and so on and so forth. But after this, in chapter okay, start from now, if I'm not mistaken, so start from this question, and chapter 2 and chapter 3, we are focusing on some kind of this question. We are
Yes,
trying.
certain topic.
Okay.
That will be easy to focus on, but as you said, from 1 to 10 is too wide. Different.
Yes, that's okay. You need to walk before you could run. That's the idea.
Oh, thank
Okay,
you.
because in chapter 1 we are teaching, we are learn about the properties of fluid. That's why I want you to know, because you know, taking subject for master is not only to pass the exam, because our nature in UTM, we would like to let students know how to conduct their master project. If they take fluid as their master project, they know what to do, and so on and so forth. They know where to find this kind of might be that it's not straightforward. So what we learn in the class, but you know the range to solve the fluid mechanics problems. That's the idea we would like to know, actually. Okay, we
Okay,
cannot just go just to answer this question and then you pass your exam. No, that's not the answer, because your in this COVID era, your final exam will come with the open-ended question. Okay, you need to prove that your answer is correct and can be used. That's the idea.
yes, we want to understand. That's all.
Okay. Okay, in 1 to 10 is actually we're talking about the fluid properties. If you read the textbook, the chapter 1 is actually about the fluid properties. So we're talking about this and that and so on and so forth. So it's quite wide range, is okay. And now we are focusing for the Navier-Stokes equation. So Navier-Stokes equation is actually more on the development of the velocity profile. Okay. Is that okay? I'm still
Okay, doctor,
answering your
okay.
question. Okay.
It is okay. Thank you.
Okay, so you could have this one. This is the velocity profile. So you know what how to solve this one. So you have the B and A here, the unknown. So we try to fix the we try to get the value of B and A here. So we are using the boundary condition. So we substitute the value of y0, u0, and yh and v is equal to capital V here. And finally, you will get this final equation. So u is equal to capital V over h y. Okay. So, and then if we try to find the value of velocity at midpoint, so we just give the condition at the midpoint, at the center point. So we put y is equal to h over 2. And we found that at any condition, okay, the flow at the midpoint is actually v over 2, means the highest velocity divided by 2 is the midpoint velocity. So in this question, okay, the question is asking about the n equals 0.5, 1.0, and 2.0. So I will answer it in the later equation, because the later question start with the proper question. Okay, so but the answer is actually, if you want to solve this one, any term of n here, any term of n means that whether this fluid is Newtonian or the non-Newtonian, shear thickening or shear thinning, actually the velocity profile is still in linear motion. Okay, that's the answer actually. That's why whether you are dealing with the Newtonian or non-Newtonian fluid beside these two, okay, your velocity gradient will always linear. So that's why you could ignore the existence of value of n here. Okay, so I will go in chapter 2. We are talking about the n later on. Okay, okay, so means that please make sure that you could do the integration, and then you could pick up the boundary condition very well. So then you could get the value of constant, and then you could come with the final answer of this one. Okay, so another things is, okay, for question 1 of 16 here. So we are dealing with the same situation of figure 115. However, so in this question, we assume that the slip velocity was occur. So as you know, if we have a moving and a fixed plate like this one, so we assume that we have a no slip condition, and then it will create the velocity at the fixed plate here is equal to 0. So means that the molecule will stick very hard on that surface, and then there are no slip. Okay. However, in certain situation, you will have the slip condition actually occur. So when the slip condition is occur, now your velocity distribution is actually cannot be like this. So you need to calculate, you need to show your velocity distribution is something like this one. So means that at starting point here, so the molecule here is not stay at their place, they also move at certain velocity. So we assume that this certain velocity is actually delta U. And what happened to this? Because if the molecule here is showing a slip condition, mean this molecule will show, it shows that that molecule will have some behavior not to stick on the surface. So it can be happen, depend on two things. One is the properties of your fluid. So now we could engineer our fluid, we add something and so on and so forth, or we could engineer our surface here. So if you do more research, you will find that nowadays if you have a nanoparticle coating, so it will reduce the no slip condition. So means that the molecule will be flowing on the nano coating, because the molecule cannot stand on the surface anymore. So means that the molecule is also will not stick on this surface very well. So previously, if this molecule stick on this surface very well, so this molecule will flow at the same velocity of this moving fluid, moving plate. So means that if this moving fluid is moving with certain velocity, let's say v, so the molecule is also moving at v velocity here. Okay, but if this fluid has a potential to slip when it's moving, so we need to draw our velocity distribution, okay, like this one. Okay, like this one actually, to be precise. So if it can slip with delta u here, so means the velocity at this point is actually reduced by delta u. So it is not create because this molecule is moving at certain delta u velocity. It doesn't mean that this molecule will move faster than the sliding plate. So this is the sliding plate. So it's slide with v velocity. It doesn't mean that we add delta u at the bottom here, because it's become 0 to delta u, but it doesn't mean that the molecule will here will move faster than the sliding with the moving plate here. So means, but the reality is the velocity actually become slower of delta u. So the idea is simple. This is actually the usage of relative velocity. If you because this molecule has tendency to move at certain velocity, and at the same time the plate is also moving at certain density at certain velocity, so it's moved in same direction, so it will reduce at this level, at this amount of delta U. So means that the idea of delta U is, so we have the L and du over dy. So the L is actually the distance of the slip condition. So, and then we need to show that the shear stress is actually mu v over h plus 2L. And the L here is the mean free path of the fluid. So, and then it can be shown, we have the equation of L later on. Okay. Okay, so we want to show that the shear stress here can be shown of this one. Okay, so and then so the slip condition of the wall is given in the textbook as du equal L du dy at the wall here. So this wall is referred to the fixed plate, and the L here means the mean free path of the fluid. And then the mean free path is the average distance traveled by a moving particle between successive impacts. So actually, it is the distance of this one actually in this physical meaning. Okay, so and then we assume that velocity profile is linear. So it is because it's referred to the previous question. So whether the n there means the du dy. So normally we have mu equal we have tau equal mu du dy. So actually for Newtonian, so we assume that n is equal to 1. So n, it can be less than 1 or more than 1. So it's referred to the shear thickening and also or shear thinning fluid. Okay, so and if you do this, whether it is equal to 1 or not, so you will get the linear velocity profile. So that's why we just make assumption of velocity profile is linear. So and then we start with this a plus by, and then I think this equation is similar from this previous question. So and then we put the boundary condition. So for example, at the bottom plate here, so the velocity is actually delta u, and then at the top velocity here, so it actually capital U minus du. So it is because, as I said here, the at the top plate here, the velocity will a little bit slower. Okay, so and then we solve the problem by using the idea of this one. So start of this one, the u dy. So we just arrange, so at u equal to 0. So we have the delta u at y equal to 0. So and then we have a plus by at y equal to 0. So and then we substitute the value of du. Okay, here. So this is come from the equation that we have here. Okay, both of this one. So and then okay. So and then we could rearrange the equation. We substitute the value of y equal to 0. So we get a is equal to a equal to lb. So and then for the second equation, so this is for the top plate. So the coordinate or the location is y equal to h. Okay, so and then we substitute all the value. We could do the integration part here. So and then integration, the differential process here, and then we could get the b is here, and then we substitute with the a, we got another a and b, and finally we could write the uy is equal u l plus y over 2l plus h. So and then we are going to calculate. Okay, the question here, if you alert, is the shear stress, not the velocity distribution. So what we get here is actually the velocity distribution, and we could calculate the shear stress tau is equal mu du dy. So and then we substitute the value of du dy here. We know the value of u, so we differentiate with dy, so we get of this one, and then we could get that at the bottom, okay, the shear stress is mu u over 2L, and at the top bottom, mu is actually mu u over 2L plus h. So we prove that these two equation can be used to calculate the shear stress. Okay, so but normally in our syllabus, so we assume that we have no slip condition. So mean the molecule will stick together on the surface. Okay, so this is also the general equation, I think. We go with that one. We still have, it's okay. So we just go what we have here. So for example, so we have if the from the previous problem, so if the temperature, so we have a sphere size and the velocity remain the same for a flow, what air pressure will not be equal to 10,000 here. So so let's say the condition is the diameter of sphere is 1.4 centimeter, 0.01 meters. So the velocity is 18 meter per second. So the temperature is 20 degrees Celsius. So and the mu is 1.81. So it is just okay for you to just use the common dynamic viscosity for air. So and then we need to calculate the Reynolds number. Okay, so and then it's give you the Reynolds number of 10,000. And what did the air pressure? So the question is the air pressure. So now from the Reynolds number, we could find the density here. So and then we will use the ideal gas law to calculate the pressure of 60.4 kilopascal. Okay, so 120.
Doctor,
Yes.
Excuse me.
Yes.
From where we get the diameter and the speed velocity?
Okay, just assume that this is the diameter given in the question.
Assuming.
So means that in your test or your final, I will give the proper statement telling you about the diameter and velocity and so on.
Yes, the value for diameter and for the velocity you will give it.
Yes, well, it will given. It will, okay, because I just take this from the textbook. Okay.
Yes, it will be. Thank you.
Okay. Okay, so this is just the idea of the slip and no slip condition. Okay, no slip condition and with slip condition. So let's say a solid cylinder of mass M, radius is R, and the length is L, fall concentrically through a vertical tube of radius R plus delta R. So I hope you could understand this, because if you have an R here, so the capillary tube must a little bit larger compared to the cylinder here. So and then the tube is filled with gas of viscosity mu. So and then it has a free path, mean free path. Okay, and then neglect free force on the front and back face. So this means that please ignore the drag force. If you know, the cylinder here will falling down like this, and then the fluid will resist this falling cylinder, and for sure the front face here will create a drag force. So please neglect the idea of drag force of this situation. So it is the idea of neglect fluid force on the front and back faces of the cylinder. Consider only shear stress in the annular region. So the annular region mean the ring section. So mean if you see from the top view here, so we are only consider the fluid that flow in this annular section. So means the ring shape of this one. find analytical expression of the terminal velocity of fall and for no slip and with slip condition. Okay, so the terminal velocity is actually the combination of the equilibrium of weight, mg, and the shear stress forces. Okay, and then here, because the shear stress forces is actually occur when the molecule stick on this area. Okay, so this is quite easy because this situation, so the axis in vertical. Yes,
The is equal to the shear stress times A.
yes, force.
How you make this assumption?
So force is equal tau A. So we learn in the beginning of the lecture.
Yes.
Okay. So and then this assumption is we assume because we neglect the force on the front and back forces. Okay. Okay. So it means that now we only focus on the shear stress. So means that this cylinder will have weight and it will falling down like
Yeah.
this. Okay, so and then this weight is actually when the fluid flow inside to this annular region, so it will create shear stress
Yep.
on this surface.
Yep.
Okay, so you could see that this gap, okay, this gap is actually very small. Okay, that's why in the question they will give you delta R is quite small, very, very small compared to the R. You could see that if the cylinder is falling down on a very, very close tight hollow cylinder, sometimes it's the falling rate, the falling speed is very slow. Can you imagine?
Yeah.
Okay. Okay, so means
Like
that
equilibrium case.
yes, we assume in equilibrium case, the weight here will be balanced with the shear stress on the side.
Okay, I understand.
Okay. That's why we need to understand the delta R is much smaller compared to the R. But if you do it in very big, so the cylinder will falling down due to the gravity only. Okay, because the density and the viscosity of gas is very light, is very small, so it's only effect on the very small gap. Okay, so in equilibrium, so we assume that the weight here is equal to the shear force. So here, the most important thing is you need, I hope you could understand which area and which part you need to take in your calculation. So you have a cylinder here. So we assume that this cylinder is falling down at certain speed. So means that the A here is actually the A for this cylinder. Okay, so you are calculating 2 pi r, the circumference, and then you need to times with the height here. Okay, so and then we will have tau is mu du dy. So the u here is actually the v, the y here is the gap. So we have a delta r here. Okay, and then the a here is 2 pi r, means the if you see here, the radius r is referred to the radius of the cylinder, and L is the length of the cylinder. And then you could get the equation of V by rearranging the equation, and you could get this one. Okay, and then if you have a slip condition, for no slip condition, I think it is, no. This is for no slip condition, and this is for slip condition. Okay, I'm sorry. So for slip condition, the shear stress can be written as this one. So we prove this one as in previous question. So we substitute the value of tau here by using this equation, and finally we could get the terminal velocity of this one. So actually this is the idea to calculate the mu. If you see this one, if we in equilibrium, So let's say so we could find that if we know the weight of the cylinder, so mean we could estimate the vertical force that acts on that cylinder. So now means by substituting this one, the mu here is can be determined. So why? Because the value velocity here is actually can be measured. So you know that if you have the cylinder like this, so you have a very tight, so you could measure the distance from here until it's moved to this one. Okay, so until this, so you know the distance here, so you could measure the time, so means that you know the velocity, means that the only unknown parameter is actually the mu. So the mu here is the mu of the fluid inside of this. But this is a very simple assumption because we neglect the forces here, the drag force. So, and then if we want to add the fluid force here, so we could, as I said previously, we could have the value of CD, the drag coefficient for cylinder, by looking tables or by the handbook. Okay, and then we add to here. We add in shear stress, sorry. So means the idea is now you have the weight here, and then it will give you a drag force in reverse direction and also the shear force in the reverse direction. So mean that in equilibrium you need to calculate the weight, and then you have the drag force. Drag force can be calculated by CD half rho AV square. And then you know the velocity here, you could calculate the cross-sectional area of this one. You know the diameter, you could calculate the area. And then the CD, you can predict from the handbook, from the cylinder, the condition of cylinder. So means that you could get the value of mu precisely. So that is how we measure the viscosity of gas actually. So we use this one. But now there are more modern device that which is calibrated and so on and so forth. So, but this is the simple mechanism to get the viscosity of the fluid of the gas. You will get this one. Okay. So again, so this is a very wide range. So we are going about to again with gas. So we have an oxygen here. Okay, please bear in mind, so oxygen is not equal with air. So oxygen is a one gas, air is the combination of few gases. And then when you give some temperature, so it will increase, the volume is increased, that why the density will reduce. So and then another thing is about the Mach number, speed of sound here. Okay, why gas is closely related to Mach number? Because our pressure, our atmosphere is actually filled by gas. So previously might be we just calculate the Mach number depend on the speed of sound, which is around 330 meter per second. So this is a constant if you just a simple situation. So we will take the speed of sound is around 330 meter per second, but this is actually the very basic idea of speed of sound. But in very details, first we need to calculate what is the speed of sound, what is the speed of sound for that particular gas on its specific temperature. Because when the temperature increase, so the properties of gas is increased too, will change. Okay, so means that the speed of sound will change also. Okay, so please do not use this idea because this is a very simple one. So what we need to do is okay, so let's say the molecular weight of oxygen is 32. So, and then we could calculate the R is equal to 60. So normally in normal textbook, they will give you the value of R is 287. So this is actually the value of gas constant numbers for air, not for oxygen. Okay, they have this one. So and then we could get the mu here, and then we could calculate the density of oxygen at certain temperature. Here, so we get it is around 0.0158 kilogram per meter cube. So and then I think this is the common equation that you already know in your undergraduate. So the speed of sound is A. Some textbook they will use C here. Okay, so it is square root of KRT, and the K here is the specific numbers. For oxygen is 1.4. So please be careful because the value of K and the value of R here, it will depend on the gas, type of gas. Okay, if you have a handbook, for example, so they will give you depends for speed of sound, they will give you depend the value of K. So normally oxygen is 1.4. Air means the air that we inhale, we breathe now also has K is equal 1.4, but it has value of R of 287. Okay, so we substitute, we get to 327 here. So and then we could calculate the mean free path according to the textbook of this one. So we get this value. Okay, so and then we get to know the Knudsen number. So and then we get whether it is the slip flow will be important or not. So here, okay, I'm not familiar with the Knudsen number actually, but we could say that as I said previously. So there are a lot of dimensionless parameter. So if possible in your study, in your research in fluid mechanics, please try to get the proper dimensionless parameter to represent your works.
Doctor,
Yes.
excuse me. Can I please go to the previous page?
Yes.
Yeah, the information here, the molecular weight of the oxygen and the mu, they got it from the table A4, right?
Yes.
A4 mentioned that the properties of common gases at 1 atm and 20 Celsius. Here
Okay.
we just have 20 Celsius, right?
Okay. Yes.
So can we take it if we take it from the table A4, if we just have 20 Celsius in our question?
Okay. So you means that table is only for 20 degrees Celsius.
The information here is from table A4, but the table A4 mentioned that it is the properties for common gases at 1 atm and 20 temperature. We have two terms, temperature and pressure.
Okay.
Here in our question, just we have temperature. Is it okay to take it, the information from table A4?
Okay. So if you calculate very specific, it is not okay because you need to, because in previous question, okay, in previous question we I give you hint how to calculate the gas with the different temperature, with the different gas, with the density, with the different temperature and so on. So if you want to calculate it very precisely, so you need to make sure that your properties is actually suit with the condition. So means actually for this one, 1200 Pascal absolute is actually a little bit a slightly vacuum condition. Okay, this is not 1 atm.
Yes,
Okay.
right.
Okay, so this is a 20 degrees Celsius. So means that if you really need a very specific answer, so you need to get the mu here for the temperature, for the pressure, and for the temperature here. Okay.
Yes.
Okay, but for because I want to talk about the speed of sound actually here. Okay, so to hint you that because in undergraduate level, I think we just use a constant value of speed of sound. Okay, I just want to mention here that in reality, in research, the speed of sound is actually varies according to the type of gas. Okay, so means that your question is if you want to get a very precise answer, yes, you need to get properties for this certain pressure and this temperature. Okay.
Yes. Yes.
Okay. Yes. If this
What
is
about Renault number? How you get? What is that equation? The 8314. What is that?
so in the textbook, in the hello, in the viscous fluid flow textbook, third edition.
Uh-huh.
I think I already upload all the table in the website.
Yeah, I saw
Yes,
the
yes, we did.
table.
Okay, for this one, for mu is a 20 times 10 by the power of 6. You can get from any textbook. It might be a little bit different.
I mean
Might be
the Renault number 8314 divided by the molecule number. Where is the
okay.
equation? I cannot
So
see.
Gas constant, this one.
so 8314 is actually the constant. When you want to
Constant. That's the constant. Right.
yeah,
Gas
this is constant.
Okay,
So
so whenever I get any of the element molecule weight, I just use 8314 divided by it. I get the Renault number of it, right?
so this is
Yeah.
not Renault number. This is a gas constant.
Oh, okay.
Okay, so the 8,314 is actually the constant.
Okay.
The constant to calculate the gas constant. Can you
All
get
right.
it? Okay.
Yeah.
Called
Okay.
the universal gas constant.
Okay. Universal gas constant 8314. Okay. And then please be careful because as I said, the gas constant R is 287 is for air. And for air here, they will take the value of A. Okay, I just forgot the value of A. It is around 40, not 44. 44 is carbon dioxide. It's 48, I think. Okay, but I will take, I will find it later. Okay. Okay,
For,
you
for the air,
you just
39, I think. 40.
40. You just replace this with 287, and
Mm.
then you will get the bottom value here. That's it.
Yeah, yeah.
Yeah, but I want to say is air is a special element because it consists of certain
Many gases.
many gas and many percentage. Okay, oxygen is might be 20% and so on and so forth. That's why
Yeah.
you need to be very careful when you deal with gas. Okay. Okay, so and okay, so this is I think we could skip. I think that we already discussed about this. Okay, 1 to 2 is about the rotating disc. But I want to say here is actually you know how to calculate the torque here. So the question is about the torque. But I want to say is if you have a situation like this, okay, you need to calculate 2 times, whether you multiple it's
Top
2
and
times.
bottom.
Because you have at the top surface will give you torque, and at the same time they will give you torque at the bottom surface. So because you need to understand that in my previous lecture, we are focusing on a singular surface. So we have this one, and then we are talking about the rotation of this one. Okay, so this is a circular. So it's rotate at certain speed, rotational speed. So when you're dealing with a rotational speed, please make sure that you convert the linear speed here with the rotational speed. So the relationship is U is equal R omega. Okay. So and then you could integrate both sides, so you will get the equation for the torque for the rotating disc, and then we need to times 2 because there are 2 surface. Okay. Okay, that's the idea of this one. So and then so I think about the temperature is I skip so everything. So this is this is about the rotating cylinder. So I think I also could skip this one. So the you need you already could answer this one. But in this question, we have the neglecting the bottom friction, and the second one is including the bottom friction. So previously in our notes, so I will give you the condition of this one. So in this situation, so the bottom surface here is curved like this, so it will create a very large gap. So as you know, is tau is equal mu du dy. So means that the increment of y here, the increment of gap here will get the less effect of shear stress. So in this situation, it is okay for us to eliminate the effect of viscosity at the bottom part. But if you have this one, okay, if you have this situation, you will find at the bottom here, they will give you a specific, a very gap, a specific gap here. So means that you cannot neglect the viscous effect at the bottom here. So what you need to do is you need to calculate this situation here, the bottom part as the rotating disc. So and then this part is actually the rotating cylinder. Okay, you need to sum all the value, and then you could get the total torque of this one. So this is just okay. I show you here. We add with this total disc, the rotation of disc and cylinder, and finally you get the total friction of this. So I think this so I skip this one because this is, I think, it is about the temperature, so we neglect it. So and then so again, so let's say we have this one. Okay, so we have these two moving plate. So we have the velocity v here, and we have fixed here. So and now we have two different dynamic viscosity, and we have the y-axis here of h/2 and h/2. So now we need to calculate the find an expression for the interface velocity u as a function of v mu1 and mu2. So we need to calculate the v here by the function of all of this mu2 and u. Okay, so it starts from the shear stress here. Okay, so and then okay, so I think we have a condition like this one from the question. Might be I'm not. Okay, let's say it's same. Okay, because it is not simple to have to make assumption of shear stress 1 is equal to shear stress 2. Okay, so let's say okay, so we know that the shear stress equation is tau is equal mu du dy, and then we could write the shear stress for fluid 1 is mu1 v minus u over h/2, because we assume that according to this diagram, okay, so the velocity at the center point here is equal to u. Okay, so and then the gap is h/2, and then for shear stress fluid number 2, so we have u minus 0, because we are talking about the u here and the 0 condition at the bottom. So we have this one. So I think the question is let's say we assume that for this question only, this is not for the general assumption. So for this question only, so let's say that the shear stress for the fluid 1 is equal to the fluid 2. So that means that we could write the tau 1 is equal to tau 2. So and then we could equalize these two equations, and finally we could get this one.